So today's class on modes on convergence. It's a very important concept for Leibniz theorem. So it's called modes of convergence. So what do you mean by convergence? Convergences are sequential convergence. So if A1, A2, An are real numbers, if they are real numbers, we call this sequence of real numbers, this converge, this sequence called converge to some L, some real, these are real numbers. We write that limit n tends to infinity a n equal to L, or we write that n tends to L as n tends to infinity. So when what is the convergence thing? For every epsilon, there exists an n0 natural number, such that whenever this n greater than n0, this an minus L, this lies between that minus epsilon to epsilon. So this is the definition of the convergence of a sequence of real number. So for the sequence of real number. Now next, if I have a set of say functions, f1, f2 is a sequence of functions, say function in R. So this converge to another function, say f. So f. So we write that fn tends to f as n tends to infinity, or limit n tends to infinity fn equal to f. If, that is if, for all x, so it has a common domain, say common domain, these are common domain. So if I have say common domain D to R, so x belongs to that D, for every x, so there is an epsilon, sorry, there is an n0, sorry, for every x and for every, or you can just say first, say every, for all epsilon positive and for all x in D, you can just interchange these two. For all x belongs to D, for all epsilon greater than positive. So these are same. There exists again n0 belongs to natural number, such that n greater than, whenever this n greater than n0, that fx minus L, oh sorry, minus fnx minus fx, this less than epsilon. So these are called pointwise convergence. This is converge pointwise. This is called pointwise convergence. So for every x and every epsilon there is an n0. So remember that here this epsilon, that n0 depends on epsilon in this case, and here it's n0 depends on epsilon and x both. So this is called say convergent in a functional convergent in the pointwise convergent. So what is pointwise convergent of function? For every epsilon or for every x, that there is an n0. So remember that n0 depends on both x0, ax and epsilon. But what is the uniform convergent of the function? So we know there is uniform convergent of the function is, again these are uniformly converge. If n converges to f for some function, uniform convergent fn tends to f, uniformly, it is called uniform convergence as n tends to infinity. If for every epsilon positive, there is an n0, so it's just interchange that n0 part and x. For all x belongs to D, there is an n0 here. For all x, there is an n0, so that for all x, such that for all x belongs to D, this is happened. That so We can choose x after choosing n0. This is called uniform convergence in D or on D, uniformly on D. So these are the idea of uniform convergence. And for next, there in for the metric different general metric space. In general metric space, if a distance there's a metric. So this is a metric space. Say M is X is a metric space with metric D. D is a metric or distance. Then in general metric space, say A1, A2, these are the elements of this X, and we say An tends to some L. L is in X as n tends to infinity. For all epsilon positive, again for there exists an n0, so a natural number, such that so everything is same. The difference is not that the different mod value of this is the distance between these two, An and L. This is less than epsilon. Sorry, for all n greater than n0 here. Here also for all n greater than n0. This is true for all n greater than n0. So distance between an and L is less than epsilon. Similarly, you can think set of all functions, and then you can think the convergent in the function space. So convergent in the function space is same as a set of all functions. You can define a metric on that. There are different metric on set of functions. There are some continuous function, integral function. There is distance between f and g is just the integration mod value of g minus x x dx. F minus g x dx. So mod value of that mod of fx minus gx dx. There are other convergence also. Sorry, LP, L2 convergence, L infinity convergence. There are norm also, different subnorm or norm linear space. So these are the idea, and we generalize this idea to the random variable. So random variable also a function. So random variable also a function. So there are also different type of convergence. So for random variable, so now go to the random variable part. Random variable. So go to the random variable part. Now, say there is a sequence of random variable. For sequence of random variable, is a corresponding distribution function for the random variable. So let this is sequence x1, x2, xn sequence of random variable. x1, x2, xn are the sequence of random variable, and the corresponding sequence of random variable with corresponding distribution function say f1, f2, so xn has the fn is the distribution. Xn has distribution function fn. Remember, fn is a function. Fn is a function from R to R to 0 on actually closed interval, and xn is also a random is function. Random is also a function, but there is a probability attached on that. So xn is a function with some underlying probability, and distribution function fn is just a function. It gives actually the outputs are the probability. So fn is sequence of distribution function, and say if there exists a distribution function, say f such that this fn x tends to fx as so fn tends to fx as n tends to infinity. So it is actually pointwise. So for every x, such that this there is fn for there is an for a given fn is a given f1 f2 fn given to you, and there is a function f is another distribution function such that this fnx goes to that fx. So it is a real number. Remember, the fnx is a sequence of real number. F is the sequence of function, but fnx is a sequence of real number. It goes to the tends to the real number fx, and it is true for all x. For all x, where it's not for all x, just for all x at which that f is continuous. So only at which where f is continuous. At the point of, it's called point of continuity. At the point of continuity, continuous, if there is a function such that fnx goes to fx tends to fx as n tends to infinity for all x at which f is continuous, in that case it is just a pointwise convergence. We call convergence, we say in this case, we say that fn converge in law or in distribution. Law or in distribution. Sometimes distribution is called law, or called weak convergent, weakly converge. So weakly converge. So these are called weakly converge. We write different notations are there. Sometimes we write fn tends to f weakly, so it is w as n tends to infinity, or we can write just fn tends to in law. Sometimes it's called law. Let's skip till as n tends to infinity. These are the notation. Sometimes we write fn in distribution. So in D, these are the same thing as n tends to infinity. So this anyone you can just use. So remember, this is a pointwise convergent of the distribution function. That's why it's a weak convergent. So, and the similar idea for the uniform convergence. So that is a strong convergence. So is the one type of convergence distribution, because a distribution function converges. So that's why we call the distribution convergent distribution. So example, we have a very simple example. So one example is this. So consider this distribution function sequence of distribution function fn. Fnx is just 0 or 1, 0 when x less than n and is greater than or equal to n. So it is distribution function. You know, distribution function is just increasing, and that as left hand infinite limit is 0, right hand infinite limit is 1, such a way, and the right continuous, everything is there. So these are the distribution function. Now question whether this has this converts to any distribution function or not, whether this is this random variable whose distribution function is fn is converts to a distribution function or not. Now what is the limit? So what is the limit? Now clearly fnx tends to 0 for all as n tends to infinity for all x. So for every x, this is actually this goes to 0. So once you fix x, fixing x, say x equal to 500. Once n tends to infinity, that means n goes beyond the 500 is actually equal to 0. That means fn goes to the function 0 function, say 0. So 0 is a 0 function. This 0 and the PPL 0 is different. The PPL 0 is the 0, real number 0, and this big 0 is the function 0. What is the function 0? The function 0 is, this is 0 for all x. So this is a function 0. Remember, you should distinguish between the function 0 and 0 function and the 0 real number as n tends to infinity weakly. So this is weakly. Sorry, you can't say it is weakly because this is not a distribution function. Remember, this 0 is not a distribution function, but the 0 is not a distribution function, which is not a distribution function, which is not a distribution function. So there is a so this is a sequence of distribution function whose converts to a function, but which is not a distribution function. So this set of sequence of distribution function does not converge anywhere. with. So another example. So another example is this. So this is a very important and interesting, useful convergent thing. This is let so x1, x2, xn are random variable with the common density. That the given density is there now, not the distribution. The density is given to us, that IID. So x1, x2, xn are IID, the same distribution, IID. So what is the distribution? It is 1 by theta. So it is uniform between 0 to theta and rest. Otherwise, it is 0. Otherwise, it is 0. Now, this theta must lies between 0, must be positive. So theta must be positive. Now, what is this? So this is a random variable whose distribution common IID random variable with the common density. Now, take Mn is the maximum value of that. So take Mn is the max of this random variables x1, x2, x3. It's maximum value of this, and we know that this maximum value of this has a PDF, which has a PDF density function. Say we write is the Fn, Fmn. X is n x to the power n minus 1 by theta to the power n when it is lies between 0 to theta, and otherwise it is 0. So otherwise it is. So this is the density function of the maximum of all the random variable. Now this is a density function. So what is the distribution function? So df of Mn is just say capital F n x. This again has 3 values. So it is before 0, it is 0. After theta, it is 1. And lies between 0 to theta, it is x my theta whole to the power n. So this is a some sort of uniform product from IID uniform. So we know this is the distribution function of the maximum value. You can easily check that. Now, what is this is a sequence of random variable and is a distribution function. What is the where it is converged? Clearly, this converge as n tends to infinity is converged to a function f(x). The function must be like that when x less than theta, that is goes to 0, because x by theta whole to the power n goes to 0, and when it is greater than or equal to theta, obviously it is 1. So this is a distribution function. So now this is a distribution function as in the previous case. So then we call this Fn converges to that f. That f, now this f is a distribution function weak convergence L tends to. So this is the example of distribution function converts to a distribution function. Sequence of distribution function converts to a distribution function. And the previous example is a sequence of distribution function which converges pointwise, but that pointwise convergent limit is not a distribution function. So there are several other examples in book. Next, there is the important theorem. So these are a very trivial or easy example in this distribution stuff. Now we have an important example. So a theorem. The theorem is let xn be a sequence of integer value, So it's take only integer value, random variables. Also let fnk equal to probability of xn equal to k. Is k equal to 0 or 2 ... be the PMF. So it is an integer value, so it is called a PMF. Be PMF of xn, the random variable xn, n equal to 1, 2 ... any positive integer, and that fx equal to that probability of x, some random variable x, equal to k be the PMF of x. X is another random variable. Be PMF of. So there is a sequence of random variable x1, x2, xn, dot, 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 and there is another random variable x, PMF of x. Then, if this PMF converges to the PMF of the x for all x, and that then this if and only if that both side implies that x10 converts to weakly, that in law to the x. So if the PMF converges, then distribution function converges. The distribution function converges, that PMF converges. This is a very important idea. So similar for the continuous case, we just omit the continuous part, and this proof is very trivial. You can easily prove. The proof is easy. You can check given PMF, it is a distribution function also converges pointwise to a distribution function. But this continuous case is slightly calculative. So we omit this continuous part, but the continuous case is also similar. For if this is a continuous thing, then one more important for continuous part, this one extra condition is needed, that let xn again xn x1 x2 xn dot 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 be, and these random variables, and the x is also another random variable. These are be continuous random variables. All are continuous random variables. So the sequence of continuous random variable and x is another continuous random variable. Then we so happen that a sequence of discrete random variables tends to a continuous random variable. That also happened, but here we assume that everything is continuous random variable, such that fn, that PMF of xn goes to fx, that is the PMF of x. Here what is this? So here that fn is small fn is just a PMF of the xn is PDF of xn, and that f is PDF of x. Then if fn x goes to fx, now is it for all x as n tends to infinity? Then we call xn then in law this x. Then we say this random, the random variable is in law. So random variable in law means a distribution in weak convergence of the distribution. So the random xn goes to x in law, or that corresponding distribution function goes to the corresponding distribution function in weakly, if and only if this PDF so goes to the PDF, converts to the PDF. But it is not true that for almost all x. It is just for almost all x. So it's actually for almost all x. So what is the meaning of for almost all x? So this is actually the almost all x. All for all, not for all, sorry. For almost all. So what is the meaning of for almost all? So what is the difference between almost all and for all? So this is the difference. So difference between difference between almost all and all. So what is almost all and all? So for all means say there so D is the set, D is in the domain set. So all means it's all for all, and almost all means so the the x belongs to D, which satisfies that thing. That if x satisfies something, some property P. This is a set. So this is, remember, this is a set. So this is a set, subset of D, and that probability is what? Not the whole set, but the probability is what? That is called almost all. Almost all means this, where this does not satisfy the condition, the probability is 0. With the null probability, this does not satisfy. So with probability 1, this satisfies. It may not be for all x, but with the probability 1. This is also called with probability 1.